for Design Automation, which was actually funded in March 2022, so it's a pretty new chair. It's essentially Robert Wille, was a full professor in Linz, who got appointed to TU Munich to lead this new chair. I followed him suit, and I'm a postdoc there now since, must be like 2.5 years roughly. At that chair, I'm probably most known for make it work for your machine, but I can also talk to the people that actually develop applications and ask them, hey, what do you need software-wise? Within that endeavor, one of my main focus points is actually the development of what we call the Munich Quantum software stack, which is basically our end-to-end workflow for making quantum computing work, hopefully, eventually, at some point. And we are the main drivers. We, speaking as Tom, Chair for Design Automation, Tom Kapp's chair, which is led by Martin Schulz, and the Leibniz Supercomputing Center. These three parties are the main drivers behind that software stack effort and pushing that forward. When you look at quantum systems, the tasks are roughly similar. You still need to be able to simulate a quantum device. You have a compilation task that is more or less on a very abstract level doing the same thing. You have verification questions, you have application questions. So the tasks themselves are kind of similar, but the kind of paradigm behind that and the complexity that comes with it is just a bit different. So in quantum computing, there are lots of question marks for all of these elaborate design flows, for all of these tools, for everything that we need to develop proper applications for quantum computing. While there are initial solutions, of course, like there is Qiskit, there's Cirq, there's PennyLane, there's all the different academic tools. It's not yet where the classical IT infrastructure really is at the moment. One of the main reasons for that is if you briefly look at that large pie chart, which was a study we did at our Munich Quantum Software Forum that we hosted last year and in 2023, where we brought together, so it's called the Munich Quantum Software Forum, so the intention was to bring together people working on quantum computing software. And we asked them, what is your profession? And the majority out of those people said their profession is physics, which kind of is interesting, at least to us, because software development, at least in the classical world, is led by software people. It is influenced by physics people building the machines, telling the software people the constraints they need to obey. But it is mainly driven by computer science people with the right expertise and the right background that did this for decades. While in quantum computing, it seems like this is not yet the case, and it's mostly lateral entrants that just try to make it work. And just to keep it a little bit interactive here, maybe a quick show of hands. Who in here would say they're more a physicist? That's actually the majority in here. Who of you is actually working on quantum computing? So it's even more drastic than that pie chart probably. Who would identify themselves as a computer scientist? It's like 2 out of 20, roughly. So I'm not saying that it's bad, and that this is nothing against you at all. Like, it's important to have people working on this topic. It's just like, there is a group of people that has decades of experience in building such similar systems. We should maybe be using that expertise in a complementary fashion to what is being built at the moment. So if we take it back, we're here, and in general, these developments are at the very beginning. But if we don't invest in them, if we don't bring in the right expertise, then we might as well end up in a situation where we have quantum computers, we have beautiful hardware, we have powerful hardware, but we can not do anything with it because we don't have the software tools to develop any applications for them. So if the hardware people continue to improve as they do at the moment, which is phenomenal to see, but we don't develop the right software for that, yeah, we still gonna not get any use out of a quantum computer. So, what's the main problem for that? Or one of the main problems for that is not only that it's maybe not enough right people working on the domain, it's also that this field is very academically driven. There are only so many industrial players working on the topic at the moment, and there's quite a bit of academia working on that. And what academic software, the result of all those papers, typically does is novel ideas, it solves great problems, it solves them with impressive results. That's basically the given. That's your goal also when you want to do a PhD, when you want to get published. That's what you do. You need to present novel ideas, and you need to be better than what was there before. But typically, it stops there. And these software tools that you develop, they're only prototypes. They only work in that specific scenario that you evaluated for your paper. That is it. They cannot be easily extended to other use cases. The code, if it is provided, it's still an if, not all is open source, is probably hard to use by other people, and most of the time it's just not documented and not maintained. I'm pretty sure everyone in here has had that situation where you read a paper, you think like, hey, cool method. They even link to source code, you click on that repository, and it says last commit 5 years ago. And you think like, oh boy, how am I supposed to run that? And that per se is also not bad. It's kind of natural in the PhD environment. This is not, the bottom points are not a priority for getting a PhD, but they're very much a priority when you want to create industry-grade software that is actually used in production, that is used to do something actually useful. And typically the characteristics that go with that is you have a full implementation, it is actually developed to be used by others, not just for creating numbers in a paper, and you have testing, you make sure that this works for others, you have documentation, and also you follow certain standards that are just established in the community. And that all might sound very clear to people, but the difference between the two worlds is quite drastic in practice, as we notice quite often. Back to the actual topic of what we do, is we are developing the Munich Quantum Toolkit as a collection of tools that tries to make possible what we take for granted in conventional IT for quantum computing. We try to take great academic software, great ideas, implement them, develop them, and also move them more and more to this right side of really industrial grade software that you can use, that others can use, that others can build on. And we have quite some history by now on actually making that work. So the Munich Quantum Toolkit, under that name, has been around since the foundation of the chair, so since March 2022. Its origins go back to my Linz days, which is, it's basically 6+ years now. So some of the software tools in there have been around for 6+ years, which is kind of cool to see with active commits, like not with last commit 6 years ago, but really with active development going on. And that is what we stand for. And now in a little more detail, what does the Munich Quantum Toolkit cover? Our goal is really to support end users in developing their applications, not particularly developing the applications themselves, but once someone has their application, making it as easy as possible for people to compile that down to a certain device, maybe even to help them choose the right device to use for a certain application, and then to execute it and decode the results. So basically to shield people as much as possible from all the intricacies of quantum computing. That goes down to actually supporting the development of hardware. Co-development was mentioned in the introduction, something that we very much support, this kind of, you develop software that makes it easier for hardware providers to test different settings, to evaluate, hey, should we be going that way or should we be going that way? Also where software can help you quite a bit and reduce your costs substantially. But we also cover basically all the steps more or less in between. So you don't have to read that in detail. I can also give you the slides later on if you want to read up on that. But it's about classical simulation, it's about compilation techniques, about verification, also error correction, an ongoing topic that is becoming more and more interesting for people, getting more and more steam. All of these steps are supported on our side by our expertise in data structures and core methods. So it's really about taking the computer science expertise from decades of building classical software and building that into tools for quantum computing. I'll walk through some of those tools. I'll give you a glimpse of how that might look like, how you can take classical techniques, apply them for quantum computing in the next couple minutes. So far, are there any questions right now? Now would be a good time for a very general question, maybe real quick. If not, then let me start by telling you a little bit about classical simulation and what you can do there. Since most of you are working on quantum computing, I'm pretty sure you're all aware how that roughly works. I'll just quickly walk through something, starting from classical computing. In classical computing, you have on a very high abstraction level with a processor. You feed that processor with a program, feed that in, it processes it, you get back the result. In quantum computing, that's not too different. So if you look at it, all that changes is literally you have a quantum processor now instead of a classical processor. And okay, you have a quantum assembly program on the left-hand side. You still feed that in, you still get classical bits out. Nothing really changes on a very high abstraction level. Deep down in the quantum computer, of course, it works a little bit differently. And from a mathematical point of view, you have your state vector, which is normalized, complex numbers, you all know that. You have operations that can be represented by unitary matrices. And you can apply them to the state, and you get out a new state. Pretty simple, pretty basic. You can actually build classical simulation out of that, because what you do is literally you start with an initial state. For every operation, you apply that operation. In the very end, you get a final state. Measure that state. You get a certain output with a certain probability dictated by the entry in the state vector. And you do this over and over again. And that's, on the one hand, how you can do classical simulation. But on the other hand, it's also more or less how a quantum computer works. You start in an initial state, you apply every operation in your program, you measure, you repeat this. And I'm pretty sure all of you in here are aware of the catch. This sounds so easy, but the catch is, of course, for n qubits, this state vector has a size of 2 to the power of n. It scales exponentially. Exponential scaling is, since COVID, a much more well-established term for people. People have a much more better grasp what that actually means to scale exponentially. I just want to drive that message home, what kind of complexity we're talking about here. So for a 2-qubit system, you can literally compute everything by hand. We're talking about 4 complex numbers, you multiply them with 4 times 4 matrices, that's it. For 12 qubits, still fits in the most efficient cache of your CPU, all good. Even for 22 qubits, probably most bigger CPUs can still fit that in their cache, so not a big deal. For 32, you're already at the limits of that MacBook, for example. So I would probably struggle to construct that state vector if I would just represent it as an array. For 42, you're already at the limits of an HPC center. And drive that up 1 or 2 or 3 more qubits. I think the largest reported number for real state vector simulation was 45 or 46 at the moment for the largest supercomputing cluster. That is it. You could double that cluster and you would get 1 qubit more, maybe. So at the moment, 305 is roughly the number of atoms in the universe. IBM's latest system has 1,000 qubits. You can imagine how high that complexity goes. And the question is, of course, how could you tackle that on the classical side for simulation? One of the answers there is design automation. So similarly to how people tackle the complexity on the classical side of things, where it might not be as drastic, because we're able to design larger systems than just 305 components, but still, we can use the same techniques. How many of you in here have heard about decision diagrams, binary decision diagrams? Quick show of hands. Most of you actually. Okay, that's good because then I can skip some of the parts or can walk you through that rather quickly. You can apply that idea to quantum computing. If you start with a state vector, what you see here is a 3-qubit state vector, so that's 8 entries. What you can do is you can split that in half. And you can form a top node out of that with 2 successors, left successor, right successor. The left one indicating that the topmost qubit is 0, and the right one indicating that the topmost qubit is 1 in all those cases. You can repeat that process recursively and break that down. Again, 2 nodes, in total 4 successors. Now, this qubit is always 0 here, always 1 here, always 0 here, always 1 here. You do this again and break it down until you have individual root nodes that just contain complex numbers. By now, you've not really gained anything, you've just given the problem a little more structure. But what you can now do is, first of all, you can extract information out of that. So if I want to arrive at that amplitude down here, I start at the top, I go down, go right, go left. So I want to arrive at 0, 1, 0, so I go left for 0, right for 1, left for 0, and I'm down at that number. So far so good. But what you can do with that structure, with that tree structure, similarly to binary decision diagrams, you can exploit redundancy in there. So let's look at a particular example of a state. Random state, randomly chosen. Maybe not so random for the example, but still. And what you can see is that here, there's only zeros, and here we have zeros. And there's no real need to represent these zeros. So we can make that whole thing a sparse data structure by just eliminating everything that is 0 and just annotating it with a single stop, saying, hey, everything that comes here, 0. That already saved quite a bit, eliminated that node down there, and eliminated the need to store some of the edge weights. Now, if you look at the right-hand side of this picture, those two, they look actually identical, structure-wise. So what you do in binary decision diagrams as well, is you combine these two together, because they have the same structure, they represent the same thing, so why store them twice? Might as well exploit that and combine that. Already quite a bit more compact. Over here, what we can do is we can pull that up, this bottom edge weight, let's go back once. We can take these leaves and pull this up into edge weights in the diagram. And now we can define some criteria for how these edge weights are normalized. And for example, I won't go into the details how you do that, but you can normalize these, you can pull edge weights up, you can do this everywhere here, and what you essentially end up with is a decision diagram that roughly looks like that. also normalized. This has quite some cool characteristics because you can sample from that data structure now by just looking at the node, looking at its two edge weights, taking the square of that, and as you can see here, if you square that, you get 2 over 10, you get 8 over 10, which literally means this qubit is in 20% 0 and in 80% 1. So sampling something from that state is literally just rolling a die that needs a value between 0 and 1. Looking at the two numbers, if it's below 0.2, you go left. If it's above 0.2, you go right. And the result is 1. You go through the tree from top to bottom, roll a die at each level, and you get a sample out of there. That's as efficient as it gets. That's basically constant time. It doesn't depend at all on how large that tree is. Just go through and sample. Sampling, of course, isn't everything. You need to do a little bit more to do classical simulation. The basic things you need is you need to be able to represent vectors. You need to be able to represent operations, matrices. There it works pretty similarly. Instead of just having 2 successors, you have 4, each quadrant of the matrix. You need to do matrix vector multiplication, or even matrix-matrix multiplication is helpful at times. You can essentially recursively break that down. Quite cool. You never need to go back from the decision diagram to the vector or to the matrix to perform these operations. If you just look at this recursive subdivision here, you can break the multiplication down, the multiplication of a matrix and a vector, into 1, 2, 3, 4 submultiplications and 2 additions. And the components, so this, the top component and the bottom component, are literally just, if you look at that node, it's the one successor and the other successor. You break that down recursively, and you have a beautiful scheme to compute all different kinds of operations. Multiplication, addition, inner product, product of product, outer product, you name it. So multiple different options. All of that is open source. So there's an open source reference implementation of that concept in our MQT core library, and you can use that. So with that, classical simulation, not a big deal. Can do that, well, it's still a big deal, it's still a complex task, but you can solve it for certain problems drastically faster than before because you can exploit some redundancy in the states. You do not need to represent the exponentially large state at all times, and that certainly helps. If you want to use that, that's one of the tools we built that's part of the Munich Quantum Toolkit. It's called MQT-DDSim. Simple pip install away, so just type pip install MQT-DDSim and you're already there. And if you're used to Qiskit, for example, and how you simulate a circuit with Qiskit, it's actually, well, literally a one-to-one replacement. You define your circuit, looks like the one on the right here, pretty basic circuit. You get a provider, which is our provider and not the Qiskit provider. You get a backend from that provider, and you type backend.run, and that is it. Literally same syntax as you would be using in Qiskit. What you get out of there is, in this case, the state vector. You could also get counts, you can also use different backends, all you want. So you can literally play around with that, and the important point here is decision diagrams as a data structure are not the silver bullet for classical simulation. They are not solving all simulation tasks faster than any other method. Otherwise, we probably wouldn't be needing a quantum computer at all if we could simulate all circuits classically. Quantum computer would be useless, right? But they're a complementary alternative to existing data structures, and it's just as easy as that to try them out. So if you have a use case where you need to classically simulate, which there are quite a few, give it a try. It is worth a try, playing with different data structures. Also small, I don't have that in the slides, unfortunately, but we also just released a new library that is not based on decision diagrams, but on tensor networks. It's called MQT-YAX, or yet another quantum simulator. If you Google that, you'll definitely find it. It's still in a bit of active development, so a couple of rough edges there, but if you're interested in another data structure for classical simulation, feel free to have a look. Those of you with a physics background are probably much more familiar with tensor networks than with decision diagrams. One of the important points that I also like to stress is that we are not trying only to build high-performance software, but also to make it accessible to people. And we built a web-based tool, it's called DDVis, that you can find under that link, posted on our website, that lets you play around with decision diagrams as a data structure. And what it basically allows you to do is you put in a circuit, there are some predefined ones, some example ones, and then you can literally, like in a debugger, step through the circuit, go forward, go backward, see how the decision diagram looks like, see how the state for that looks like, and play around with certain algorithms. Gives you a bit of a feeling of how that data structure works, where it does not work. Kind of, most of the time it's understated that these educational efforts are also important to get the broader community involved with these topics and to get people more involved with these rather computer sciencey topics. But so much to classical simulation. Big and important part in making quantum computing work is also compilation. I was always kind of surprised that this is not so well known, that there's quite a bit going on from you write down your quantum program to that quantum program actually running on the current quantum computer. Most of you in here probably are well aware of that. I'm still going to go through a couple of steps here, but in the wider community, that is still just, yeah, I sent it to the Qiskit provider and it yielded bad results. Okay, what's going on behind there is, let's draw again the analogy to classical computing. Pretty sure no one of you is writing assembly programs anymore, hopefully. How many of you still are? Any? All right, I figured. What most people probably do on the classical side of things is they write things in C++, in Python, in Rust, in any high-level programming language. They don't go down to the machine level, go down even further, but they don't go down that low anymore. And then the compiler takes their high-level program, compiles it down to something the machine understands, executes that, you get back results. These compilers have also been developed for decades, they're performant, we use them on a daily basis, essentially, even if we don't know about it. We don't even feel it. In quantum computing, situation is again similar. You're probably not writing CASM files. I really hope you do not do that anymore. 5-6 years back, that was still a common practice, that people would literally be writing text files and submitting those. Right now, at least, we have high-level SDKs, such as Qiskit, Ticket, Pennylane, and so on and so forth, and they have compilers that break the high-level program down into something that can be run on the quantum computer. Just to give you a glimpse of how complex that could look like, I'll show you a sketch from January 25 from an event in Dublin with HPC people. So this was with a high-performance crowd, talking about the different levels of access. You don't have to read all of that. You don't have to understand it in detail. It's just the sheer complexity of a domain expert on the top left specifying a program and that going through some kind of translation for it to be actually executed. And I'm quickly throwing that away again, because please don't look at that too much. But it is a complex task that people are thinking about. In very simple terms, compilation of quantum circuits is you take an algorithm, you have a limited gate set. Your quantum computers typically have single qubit gates and 1 2-qubit gate, maybe 2. So you need to break gates down in the synthesis process. Then most of the systems also have a limited kind of connectivity. So in this case, it's a linear chain of 4 qubits. You need to perform some kind of mapping task where you assign the qubits of the circuit to the qubits of the device, and you can execute some of the gates. Some of them might not be executable, so you insert swap gates, something different. For other technologies, and you execute the rest of your circuit. And because these devices are very, very sensitive, they are noisy, you need to keep those circuits as small as possible, so you do some optimizations that reduce the circuit size again, and you end up with an eventual realization of your circuit that the previous sketch showed there are a couple more steps below that, but in essence, limited gate set, limited connectivity, and you want to optimize as much as possible because the quality of the current devices is just not there yet where it should be. So, if we briefly focus on the mapping task, then the task there is you get a circuit that is already decomposed, you get a coupling graph of your device, and you want to make that work by inserting swap gates, essentially. And all the different techniques, they are a trade-off between either how fast they are or how good they are. So it's always a trade-off between runtime and quality. You can be very fast, by inserting many swap gates. Basically, you go through a circuit left to right, insert swap gates as you need them. It's as fast as it gets. It's also as bad as it gets. Be a little more clever, employ some heuristics. That's what most compilers currently do. Be a little bit better. Or you could even strive for the optimal solution, which takes very, very, very long and doesn't scale at all, but you get the best quality result. And in the interest of time, I'm not going into very much of the details. But essentially, what I want to show you, and you'll get the slides later on, is that you can take that problem and you can apply classical design automation techniques, in this case SAT solving, satisfiability solving. You formulate the whole problem space symbolically, pass that over to a classical solver, and let it get you results for the mapping task, which outperform quite some of the existing solutions that have been around when this was published. So this was able to show that back in the days, 5-6 years ago, Qiskit solution introduced more than double the number of swap gates that were actually necessary to compile a circuit. Again, this is part of a tool. It's called MQTQmap. It started out as a mapping tool. By now, we rather refer to it as a tool for mapping circuits to different technologies, because as I'll show you in a second, it can do much more by now. But in essence, it's similar. You describe your circuit, you describe your backend. Again, you can use Qiskit if you want, and you can compile it with a single line of Python, just specifying some options for the resulting circuit. That's it, as easy as that. What you see here is kind of the influence of what compilation really, the influence that compilation has on the performance of your device. I'll quickly walk you through that graph. You don't have to understand that in detail. What you see on the x-axis is different benchmarks chosen from our benchmark suite that are compiled under different settings, and we measure the expected fidelity of those circuits on the actual device. They're sorted by kind of the best fidelity that we could achieve, and for every data point, it shows the range of possible expected fidelity values for different compiler options. Like say, choose compiler A with option B, choose compiler B with option D, or so. And what you should take from this is essentially choosing the right options, especially on the right-hand side, makes the difference between success or complete noise. Like the worst results are literally a fidelity that is very, very close to zero, which you could just roll a die and it would be better than the result of the quantum computer. Versus if you choose the right compilation options, you actually get results out of the quantum computer and actually the results you would have expected. So compilation really is key. It's not only key for superconducting systems where these kind of connectivity constraints apply, it's also very interesting for neutral atom-based systems which have been around for quite some while but have gained significant momentum over the past couple of years. What you see here is just a very small animation of our neutral atom compiler that uses shuttling instead of swap gates and zoned architectures. This is, I think, a QAOA circuit that is being simulated. So you see single qubit layers being performed down here, then qubits being picked up, moved up, 2 qubit gates being applied in that zone, qubits being moved down again, and the computation goes on and on and on. This is just something that we've been building for roughly 2 years now, different compilation approaches for neutral atom systems. If there's more interest in that, I'm happy to take that into the discussion later on. I'll briefly skip one of the topics that is very dear to my heart, but in the interest of time, I'll not talk about verification, but you should all verify your circuits, and I'll keep it as short as we have a tool for that. If you have 2 quantum circuits, you have one, you have a second, maybe a compiled circuit, and you want to know that that compiled circuit still does the right thing, then the tool is called QCEC, and it's a single line of Python. You throw the 2 circuits in, and it tells you, yeah, they're still equivalent. Very cool for testing your optimizations and for making sure that your stuff works and that you applied the right things. Use that in all of our compilation techniques. Just make sure that we're doing the right thing and that it actually works, that you didn't perform an optimization that optimized something away that was important. Also, a very brief shout out to our MQT bench library, because when you develop software, and I'm pretty sure everyone in here that is pursuing a PhD or so has had the struggle of finding the right benchmarks for their evaluation, for their paper, for their comparisons. We've struggled with that quite a bit in the past too, which is why we decided to build a solution for it. Namely, we built a library, first of all, it was a Python-based library to generate benchmarks for various applications on various different abstraction levels. Say you want a circuit that is already decomposed into native gates of a device so that you can benchmark your mapping solution. There's a setting for that that allows you to do exactly that. Say you want circuits in a gate set that works on IQM quantum computers. There's an option for that. You can plug in a Qiskit circuit or even just a string, tell them, hey, my application is amplitude estimation, for example. I want a circuit that works on the latest IQM system. This tool will give you such a circuit. It will give you dozens of them. By now, the number might even be inaccurate by now. I think you can generate well over 70,000 circuits with that. We took it one step further because even using Python is too hard for some people. We built a service out of that. It's a web page you can access. The link is on the top or on the QR code. You can go there, and it's literally just clicking together which application you want, how many qubits you wanted, and then selecting a couple of options for the various different levels. So whether you wanted just an optimized circuit, whether you want it on a certain native gate set, or on a certain device. You click together your option, you click download, you get all your files. You don't have to use it, of course, but if you do, I think it could be helpful for your evaluations. It helps reproducibility. It helps you to show that you did this on established benchmarks, and that certainly also helps research. If there's anything that's missing in there, so like we keep growing the number of applications, we keep growing the number of supported devices, and also the number of supported compilers, but if anything is missing in there, then please just text us. So all of this is open source, you can reach out, we are happy to integrate stuff, we're happy to work on stuff, and to work with you on that. So, taking this back to the Munich Quantum Toolkit picture. This was a very, very quick overview of mostly simulation, compilation, very little verification. I could probably talk for, I don't know, for the whole day to fill you in on the rest. There's not enough time for that. If you're interested in that, there are a couple links here. You can always reach out to us. But I also want to show you that this is not only a picture, this is also really a collection of tools that is open source. I think the slide is too small to literally show all tools by now. I updated this last autumn or so. By now it's a couple more. Don't really fit anymore on the slide. But what this is to show to you is that this is a collection of actual software that you can use, and not just papers with numbers and tables of, hey, new versus old, new is better. By now, the whole Munich Quantum Toolkit has reached roughly 1K stars on GitHub, which is something I'm pretty proud of because the numbers aren't that important, but still it kind of shows that people are actually, first of all, liking the tools, and based on our download statistics, they're also using the tools. All of them collectively have been downloaded roughly 2 million times, and don't give anything on that particular number. These numbers are just ballpark estimates from PyPI. They are influenced by so many factors, but it does make a difference if there's 2 million or 2,000. So it still indicates that these tools are actively used, which I really love to see. And with that, in the interest of time, I'd also like to come to some conclusions here. First of all, I hope I was able to convey to you that software is really important. Like, hardware development is great. It's absolutely necessary, otherwise we won't get quantum advantage at any point. But software is equally important. We need to build the proper software to make all of this work. In that whole software part, compilation is really a key area, and choosing the right options, choosing the right compiler, knowing what you're doing is absolutely key and makes the difference between the successful execution or just getting random noise. That's a proven fact. We try to build tools that really cover almost the entire stack. So we try really from supporting people to supporting people trying to use the computers, people building the actual hardware. And on top of that, we also try to make that as easily usable as possible by building services so people can either educate themselves, use the tool more easily, or build on top of these tools. And with that, I think I'm right in time, and I'm open for questions right here, or to dive deeper into certain of those topics. Thanks. Any questions in the room? Go for it.
What would like a circuit look like that your decision tree simulator would be very suited for?
So I don't know if the online audience can really hear the question, so I'll just repeat the question. The question was, which kind of circuits decision diagrams are well suited for? And the thing is, that's a question that we've been thinking about for quite a while now over the last couple of years, to identify these classes of circuits where it works. Because evidentially, we've had evaluations in papers where they seem to work, but really identifying the clusters and kind of the characteristics of circuits that make it work is, I'd still say, an ongoing challenge, but just to give you some intuition, it tends to work well for things that have a particular structure in the representations of the state vector. What I'm referring to as structure is really, if you think about Grover's algorithm, for example, and let me actually go back to one of the slides I showed you from the visualization tool. Here, this is actually a simulation of Grover's. And if you think about how Grover's works, you start with an equal superposition of everything. That is as compact as it gets in decision diagram. So any product state is just a linear number of nodes. And then you apply these Grover iterations. And what they do is essentially they increase the amplitude of your desired state and collectively shrink the amplitude of all other states. That's essentially also what you see here. You have a collectively small probability for all unwanted states and one high probability for your desired state. And if you now look at the decision diagram representation for that, this is a linear representation. It has essentially two strands. One of them, now I have to pick the right one, this one is the equal superposition. You see 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, 1 over square root of 2. Square that and you have 1 over 2. So it's a 50-50 chance for each of those qubits to be 0 or 1. And the other strand literally encodes the solution. The solution in this case is is all ones. So you go right, right, right. And along by the thickness in the tree, you see, okay, yeah, this is where you would be going most of the time. It says 0.98, 0.99, 0.995 for probability here. And all the other cases lead back to that superposition strand. And this is it's a small example, and naturally the simulation of Grover's cannot always stay linear, otherwise it would be a useless algorithm. So between applying this Oracle and diffusion operation, the decision diagram grows quite a bit, but it shrinks back down again. And this is a very favorable property for an algorithm to have to make it suitable for decision diagrams. So this kind of property that the decision diagram grows, then shrinks again, and it maintains some kind of structure in the problem, works rather well. This holds. Grover is a pretty good example of one of the more known algorithms. Phase estimation tends to work quite well. Interestingly, in the case where the phase is exactly representable by the number of bits you choose for the phase estimation, the interesting bit there is this is not a factor for most other data structures. If you use a tensor network simulator, it couldn't care less about the actual numbers in your operations. It just cares about the pattern of applications of gates and how local they are and how much entanglement they create. In decision diagrams, this makes the difference between a linear size of the decision diagram and actually a worst case example. So also the particular instance of the application makes a difference. And that is also why it's so hard to find these real classes of algorithms where they work. Which is also why we keep saying, just try them. It's as easy as starting that in parallel to whatever you're doing at the moment. Just try it out. It might as well work for your use case. Does that roughly give an idea?
I would assume like in-circuit measurement would be also very useful, because then you can just throw away like...
Yes, so mid-circuit measurements, that's one of the cool things that the simulator can actually very natively do. So our simulator just supports almost arbitrarily classical feedback, mid-circuit measurements, and stuff like that, because what you essentially do is if you, let's say you measure that node here, then you roll a die, and depending on the result, you either kick out this subtree or this subtree. And that reduces your size considerably, of course. The thing is that the advantage you lose is this kind of, if you don't have mid-circuit measurements, you can simulate a circuit once and sample from the final state 1,000,000 times, and you still have only simulated your circuit once. That is something that not all simulators actually take advantage of. Many of them just simulate for 1,000 shots. They do 1,000 simulations because they can. But you can do better than that and just simulate once and sample 1,000,000 times, which is especially easy with decision diagrams. Once you have mid-circuit measurements, that is no longer possible, because each individual measurement, of course, influences the rest of your computation, so you actually need to simulate then number of shots times. But we've also did quite some experiments with iterative phase estimation and the iterative version of Bernstein-Mazzirani, which literally break the problem down from, let's say, n qubits to 1 or 2 qubits, but to n steps with mid-circuit measurements, and that works phenomenally well. So also a direction that is currently being explored on actual quantum computers and in compilation, like mostly it's referred to as qubit reuse. So how can you measure early and reuse the qubit for a computation instead of using an additional qubit? Also a very interesting ongoing research topic, where classical simulation techniques and compilation techniques actually go hand in hand. And kind of if you advance the classical simulation technique, you can probably take 80% of that and move it over to a compilation technique and make it work there. Maybe just because we have time, an interesting anecdote there is also this works for simulations on actual quantum computers and classical simulation as well, like techniques applied to the actual simulation on quantum computers, like circuit cutting, which probably many of you are familiar, like this whole notion of cutting a circuit into pieces, distributing that on different QPUs or on the same QPU but in subsequent runs, and then aggregating the results again, is something that is heavily done for actual simulations of quantum circuits on machines, because the machines are limited in size, limited in fidelity, and you hope to get more out of them by doing circuit cutting. You can apply the same techniques almost one-to-one to classical simulation, and you can even do a little bit more on the classical side because you get full access to a state vector representation, and you can kind of more or less like post-selection. You can say that, okay, I branch on the measurement, or I branch on this cutting point, and I create two sub-simulations that just the one assumes 0 was measured, the other assumes 1 was measured, and I just continue that in parallel and build kind of a computation tree, aggregate all the results later on. So it's actually one of the most interesting techniques for parallelizing classical simulation, in my opinion, especially when it comes to decision diagrams where parallelization is hard otherwise. Hope that provided some context. Any other questions?
We have a question from the online audience. Dipendra Shrista asking, do we have industrial-based use case that implemented using this toolkit?
I don't know if the online audience saw the question online, so I'm not going to repeat it. The industrial case, use case implemented with these things. I'd say it's probably a bit provocative, but at the moment there are hardly any industrial use cases being implemented for quantum computing that actually work. So that's the one statement there. It's really tough to speak about industrial use cases. Most of these are actually toy problems being solved, like literally talking about a logistics problem and solving traveling salesman on 5 cities, things like that. You could apply any tool out there to these kind of problems, and they would just be fine, probably. If you scale to real problem sizes, then one has to say there are just not the quantum computers that could actually run those real problem cases at the moment. But you can use the conjunction of tools right now to actually test whether your application would work. There's something that I haven't highlighted in here, but I'll go quickly back to the overview of the tools. And this in my opinion, belongs very much to this application side of things and supporting people in the development of applications. And I don't have the slides here right now, but the term resource estimation probably rings a bell for most of you. So like instead of working on a 5-qubit toy problem, you try to develop the problem, or you try to formulate your problem in the real world size, and knowing that there is no machine that can actually run it, you do some estimates of how big would the machine need to be, how good would it need to be to actually yield reliable results. And you can base that on certain models, on certain assumptions, also on certain assumptions on error correction. You can feed all of these parameters into a tool, and it will tell you, hey, for that particular use case, you need 1 trillion qubits with a 0.10 nines fidelity for 2-qubit gates to actually make it work. And that in itself is not yet that helpful. But what these resource estimation tools allow you, they kind of allow you to do this co-design and evolution of your approach. Because if you manage to improve your software solution so that it's now not requires 10 nines of fidelity, but you got that down to, I don't know, 7 nines, then you already made an improvement and you kind of lowered your expected timeline to probably a couple of years, because hardware will take a couple years to get that extra mile. And if you continuously use that, like resource estimation as a tool in your development, you're actually optimizing for the use case that you're aiming for, and not for the 5-qubit toy problem that will not be relevant once we have actual useful quantum computers. And this kind of premature optimization for small-scale problems is a real issue also in the community. Like, we need to build software that doesn't only work for 10 qubits, we need to build software that works for thousands of qubits. And that's also, again, where this kind of issue between academic software and industrial-grade software comes in. So if we quickly go back to that slide, it's just academic software per definition is most of the time on that left-hand side with just, experimenting with dozens of qubits on a personal computer, and that is it. But what we need solutions that scale to thousands of qubits already now. If you look at the roadmaps from IBM or from Planck, for example, for neutral atoms or for other neutral atom players, we're talking about thousands of qubits in the next 1 or 2 years. We need software that can actually handle that. And that's the main challenge also there. We're aiming for that. So also coming back to the online question a little bit more, we're aiming to build software that can actually run these applications in the future. We're building those resource estimation tools to give them in the hands of users to allow for rapid prototyping. And in that sense, I would say yes, these tools are used at the moment to benchmark and test real applications. There's a question at the very back there.
Yes. So what would you say is your relationship or vision for this toolkit in relation to other toolkits, for example, like Qiskit or so? Are you seeing yourself as a competitor or as a symbiotic relationship, codependence? I don't know.
Yeah, so the question was, how does all of this stand in relation to other SDKs like Qiskit, like Penny Lane, and so on and so forth? And of course, that comes up often. And the answer is pretty simple. We do not want to be a competitor to Qiskit. That is not. We're way too few people with way too little resources. That cannot be the goal of such an initiative. What we want to do, and that is also what we want to drive home, if you look at the second picture of that slide, namely that picture, we want to develop a collection of tools that work for the pain points along the software stack. So you have that whole big software stack with dozens of challenges that need to be solved, each of them harder than the next. And for these particular challenges, we want to provide solutions that are inspired by techniques from conventional IT, from design automation, and solve those particular tasks better, easier, faster, more accessible, you name it. So it's literally our main goal, our task is to identify these pain points, to talk with people with quite a broad network in that, ask them, what do you need, where do you currently struggle the most, and then develop tools for that. We cannot hope to develop something that literally develops the end-to-end solution that competes with a billion-dollar company. So We need to be realistic here. The thing that comes probably closest to I wouldn't even call that a competitor to Qiskit, but that is this Munich Quantum Software Stack initiative. That is this initiative of the Munich Quantum Valley of building an ecosystem within Bavaria, within Germany, within Europe, but also worldwide, that people can refer to and people can use. The unique point there is, one of the unique points is it's tied to HPC, so really to high performance computing, because we also, in the Munich Quantum Valley, we have access to multiple quantum computers actually on site. Like the Leibniz Supercomputing Center hosts, and I'm probably misremembering, but at least 2 superconducting quantum computers, actually 3. It hosts an AQT ion trap system, and it will host a Planck neutral atom machine right next to the supercomputer. And that is quite a unique situation that many other players around the world don't really have, to have this on-premise, to have this really connected to the respective compute power. Most of the other quantum computing offerings are cloud services. Look at AWS, look at IBM's offering. You log on there, you get your API key, you send your stuff there. The kind of latencies involved in that, they might be a bottleneck at some point. And you can't just build a supercomputing center around every single quantum computer out there. So the approach we're taking in the MQSS at the moment, that is probably very unique. Also something for the sovereignty of Europe in all of this, like a bit of independence maybe from players like Qiskit, from players like, also looking at things like NVIDIA, who are heavily pushing their software stack at the moment. Having a bit of German European expertise in there and the solid ground is also something that we strive for and for what we stand, which is also why it's great to be here, because there's a lot of Munich in all of these names, but don't get blinded by that. This is really also intended as Germany-wide, European-wide effort to build quantum software together and to make our point that we can actually do this and we can compete in certain areas with whatever they are doing over there. Does that roughly answer the question?
It does, yes.
We can follow up on that later on. I'm around.
Thank you. Fine.
Any further questions? Or
Okay, thank you so much, Lukas, for your presentation, for your talk, and to the audience for participating. In our next colloquium on the 10th of April, we will have Marko Rancic from the University of Luxembourg on site presenting his talk on quantum computing in physics, chemistry, and optimization. Thank you for your attention and have a nice day.
thanks, everyone.